One at a time, guys. How would you convert 15 degrees to radians? Yeah, what do you want to get rid of? What unit do you not want there anymore? Degrees. So I want to kill degrees. So I'm going to put degrees down here, and then put rads up here. So 180 degrees in pi radians. Reduce 15 and 180.
12.
Huh?
112.
112? Okay. So I get pi over 12. Oh, why am I, look at, again, I'm trying to erase the freaking mark of the cursor. So you already got this answer, don't you? How many radians per second? Pi over 12 radians per second. So you've already got 1/3 of the problem done. You're welcome. How do you get this now? What was the formula that connects this? We just talked about it. I understand that, which is why I can look at your notes. V equals R omega. Do we know R? Yes, we do. Okay.
Yep.
Right. So I'm going to leave you something to do. I'll leave you the middle dude. Yeah. Okay. Is that all right? Okay. So I'm glad you asked that question because I had forgotten to talk about linear speed, angular speed, all that kind of stuff. It's not a big focus, but it's a very useful, very often used angular idea. Okay. You gotta be, I will give you a little hint. What's the M mean in RPM again? And what's all of our time stuff? Oh shit, be careful. Okay. Anything else from homework stuff? Okay, all right. So let's do this. I want to. Let me do this first before I forget, because I'm about to shut this dude down. Let me do this. Capture this good shit on my phone. For everybody who's not here today, we discussed this. Linear speed is there. Angular speed is what angle I go through over the amount of time, so it's there. The connection is here. And then we did RPMs. 1 RPM is 2 pi rads per minute, because that's how far 1 revolution is. Okay. I just wasn't recording, so I want to make sure it gets in there. Okay. So now I got a little review worksheet from chapter 7. Some hopefully basic stuff we'll find out. So what was arc length formula again? S equals R theta. Does anyone remember the area of a sector? 1/2 R squared theta. I love it. Okay, so here we go. Not a quiz or anything. This is a worksheet so you can use notes and such. You can use other people if you want to. Don't just use them though. Ask them if it's okay. So go ahead and try these out. If you want to work with people near you, you certainly can. If you want to borrow a calculator, you certainly can. I want to tell you, for problems like this, don't do decimals. For problems, yeah, when you're finding arc length and area, go ahead and take that down to decimals, that's fine. So this is just a review of what we've done so far in chapter 7. Just one handed this out. I'm sorry. Quick question, which one of those are in radians right now? You. How do you know that? No degrees, only shit, okay. Hey.
So, if you're in degrees, you want to
All right, guys. Let's take a look here. Can somebody tell me how to set this up to do the conversion? What goes on the bottom? Degrees. And now you just reduce, right? So right off the bat, you can kill the zeros. What goes into 24 and 18? 6.
Yeah.
So you get 4 pi over 3 rads. Is that cool? Now the rad is funny. You can put it or not. Because if you don't put it, and I know it's an angle, I'm assuming it's radians if I don't see a unit. I like it. Okay. There are like 2 ways to do part B. I'll do the long way and then I'll do the short way. So if I start with 5 pi over 6 radians, I want to put radians on the bottom and degrees on the top. Exactly what we did in the first step, yeah? Just turned over, because now I want the radians to die. We put rads here, they die. But do you see how the pi will always cancel when I do that, and the 180 will be up top? So the shortcut is, right from the beginning, just replace pi with 180 degrees. Both ways will end up in the same place. What's 180 divided by 6? Divide times 5. Sweet. By the way, real quick, does anyone remember what pi over 6 radians is? We basically just did it, but 30 degrees. Can somebody tell me 5 pi over 6? How much short of a full pi, which you could use as an insult, is a little short of a full pi. How much short of a full pi is 5 pi over 6? 5 or 6 short. So isn't that 30 degrees short of 180? Isn't that 150? I mean, there's a few different ways you can look at this. Or not. And then part C, what units is it in already? You guys told me. Radians, so one, and there's no pi. That sucks. I can't just do the shortcut we just did, because there's no pi. So I want to put radians down below, degrees up top. Now this is one place where you can make a decimal, that's fine, because what do you get? You get 11 times 180, which is 1980, is that right? Yes? Divided by pi. This would be degrees, and that's very unsatisfactory, right? Even though 1980 was a great year. You know, like, it was way before I went to show. But I would go ahead and make this a decimal, because right now it doesn't make any sense. 1980 pi, what the hell? 1980 over pi. And I'm not going to try to do that in my head. Thank you very much. I'm going to say that's roughly 600 degrees. 623. No, I have no idea.
630.
Really? Okay. 630.25 degrees. Okay, so on the actual test or quiz, I tell you how many decimals to round to. Yes? Normally it's going to be hundreds, so that's pretty good. Hundredths place. So this whole first four should be relatively straightforward, yeah? So 340 degrees, just do it very quickly. Put degrees on the bottom, radians on the top. Kill the 0, divide by 2, and I'll get 17 pi ninths rads. There's no reason to make this into a decimal. Can somebody tell me if this is more or less than 2 full rotations? Look at it, 17 pi over 9. Oh man, this problem is not the best example of this, but what's a full 2 pi? What divided by 9 would be a full 2 pi? 18. So isn't this a little short? And of course you already know it's less because 340 is a little short of 360, but still. By the way, I'm sorry, the way I keep saying pi, it's related to a character from Adventure Time.
What's about the pi field?
All right, so the coterminal thing. How do you find a positive coterminal angle? How much do you go past this? Yes, coterminal just means it's going to be ending up facing the same way. So if I say somebody face Genevieve, and I say now turn and still face her, they're going to have to go to a full rotation of 360, right? Okay. So if I add 360, I get 489. How do I get a negative coterminal angle? Subtract 360, so I can do 360 minus 129. Or you can just do it in your damn calculator. So what do you get? 231? Is that right?
Yep.
Negative 231 degrees. All right, so coterminal, silly easy. If I ask you for another coterminal angle, what could you do? I want another one. I want another one.
Do it again.
Do what again?
Minus 360.
Yeah, minus 360 or add 360 to 489. You can just keep doing that until you go insane. So when I ask for a coterminal angle, you can be very creative. You can add 37 360s and get this stupid big number and say, have fun with that, Jeff, checking that one. You guys can be right. Okay, maybe. You're like, ooh, the level of creativity here is off the charts. Okay. So what about this little blue triangle, little blue? Little blue. Find all 6 trig function values, and when I say that, I obviously mean sine, cosine, tangent, blah, blah, secant, cosecant, cosecant. Be careful that it's up here. So again, if you already know some trigonometry and you know SOHCAHTOA, that's fine. You can use it. I'm not going to make you not use it. I just wish you had never been taught the damn thing. Right? Because it's bad. The only thing that it does better than my method, not my method, just the right method, is I have to turn it and say, oh, this is my y, and this is my x. This is x, and this is y. So what am I missing? Do I know everything I need for sine theta? Yeah, 3 or 4. But do I know what I need for cosine and tangent? Jeff. That'll work. What do I need to know for cosine theta? The x side. How do I get the x side? Old Greek dude. What's old Greek dude say this is?
Root 7.
16 minus 9, right? Is that cool? A squared plus B squared equals C squared, so A squared equals B squared minus, C squared minus B squared, so 16 minus 9 is 7, squared is 7. Don't make Pythagorean theorem hard. Hypotenuse is always the biggest side. So if I know it, and I'm missing a smaller side, I've got to subtract from it to get the other one. Hypotenuse is always the bigger side. If you guys want to see this kind of worked out, if you call this A, or let's call it X, because that's what the hell it is. X squared plus 3 squared equals 4 squared. X squared plus 9 equals 16. X squared equals 7, so X equals square root of 7. So what's cosine? Square root of 7 over 4. Do I have to do anything to that? No, because radical's on top. We're happy. What about tangent? Three over rad 7, and then like you said, we got to rationalize that. So I get 3 rad 7 over 7. Okay. By the way, it's not the official sound effect. You can make whatever sound effect you want. So what about cosecant? Yeah, just flip sign. What about secant? Just flip cosine. So again, yeah, you got to rationalize it. And what about cotangent? I would start with this and flip it. Wow. So never use the rationalized form when you're going to flip for the trig function you need. Start with the original, because once you flip it, I don't have to rationalize. Yeah. Is that all right? That's the brand new stuff. I've never done anything quite like that, unless you've done some trig before, in which case it's not brand new. All right, so what about this? Can anyone identify the very, very first thing I have to take care of? Yeah. Yeah. So in general, when you're not certain, go for ratings. You ask any math person, will probably agree that we wish degrees didn't exist. There's just no need for it. Ratings are better, because ratings are an actual physical measurement. Degrees are just, well, let's cut it into 360 pieces. Yeah? I don't know if you guys understand that. Okay. There's nothing special about 360 except I can cut it a lot of different ways. So we just pick that number. It's a nice number. So how do I convert this to radians? 180 on the bottom. Find the top, kill the 8, reduce it. That'll be 4 pi over 9. 4 pi over 9 rad. Don't make that into a decimal because you don't want to round until the end. If you make it a decimal, you round, your answer will be wrong. So how do you get the arc length? R theta. R is 38. Theta is 4 pi over 9. And now you can throw that shit in the calculator. Because again, if I ask you, how far did Farmer Bob walk? And you tell me he walked 17 pi over 6 feet. I'm like, who the shit are you? How far did the man walk? Let's see. 4, 16, 48. No, I'm going to say it's like 50.7. What is it?
53.06.
Oh, that's pretty good. It's good for government work. 53.05, 06, 05, 06, 06. Okay. What's inches? All right, so be really careful. I want units on these kind of problems. And if you don't put units, I'm going to be a dork. I'm going to put down here sheep. I'm going to put down here stupid things, right? Don't make me do that. Light years. Okay. Area, just got to remember the formula. And then you just plug in. R was, 38 squared. That's a big one right there. People forget to square that like I almost just did. 4 pi over 9. All right, math boy. Give me a second. Wait a minute. Let me see. 20. 1060. Hold on. Did you do all that right, Jeff? Who knows? 1060, but it's a little too what? It's a little too something. I don't know, 1060.
1008.
1008.
1008?
Yeah.
I got tired in the middle. 1008 point stuff.
Yeah,
Yeah.
0.10
10. I could have done
Square
better, but I
inches.
gave up. What would the units be?
inches squared.
Good, because it's area. Also, what am I squaring right here? 38 what?
Oh, inches.
Inches.
So of course it's inches squared, because I square the inches. But also just because it's area. So it better be inches squared. Okay, let's stop for a minute. Yeah, good. All right, I want the rest of the time devoted to something specific. You guys all with me? Please let this whole worksheet be relatively easy. Now, I understand if you haven't devoted much time to memorizing these, but again, you had your notes you can go back to, you had that worksheet to go back to. And I understand if these two are a little weird, and I understand if you're not used to changing angles to radians, because a lot of you guys didn't know about radians existing until just this semester. But relatively, this stuff is not that bad. Okay. So then you're like, let's get to the bad stuff. Okay. Not bad stuff. So what I want to do now, did we get all that stuff? I want to talk about the fact that when we created the sine, it's a function. Its outputs are, what's the input of sine? Sine, what goes inside of a sine? What do I always put inside of an angle? So whatever's inside of the trig function must be an angle. Okay. So what I want to focus on is to really make you guys realize this is a function of the angle. As the angle changes, sine will change. So let me ask you this very basic idea. Which one of these, oh God, oh Jesus Christ, which one of these, given that they both have the same radius, will have a bigger sine? Let's see if you guys get this question. Which one of those, if they have the same r, will have a bigger sine? The first one or the second one? Why will the second one have a bigger sine? Y gets bigger, yeah. So as the angle gets bigger, sine gets bigger. All right, every function we've looked at, I could say something like that about, correct? Square root of x, as the x input gets bigger, the output gets bigger, yes? And so forth. So this is definitely a function of theta, theta being the angular input. Therefore, can the square root give me different answers if I put the same number in? Can the square root of 4 be different from the square root of 4? No, okay. I appreciate that this is a weird question. That means that the sine, but can't I make this a larger frickin' triangle? Wouldn't it then have a bigger y than it did at first? But doesn't it also have a bigger r? So the ratio stays the same. I need this, let me say this again. No matter how small or big my triangle is, if it has the same angle in the base, all the sine cosine shit stays the same. In fact, we talked about that idea before. That's why I can use this as a measurement, because no matter how big or small my circle gets, the radius grows accordingly. So all the kind of ratios I can make, they are reduced to be the same thing. So if I take one situation, we're going to focus on a few angles. If I take one situation, let's say a 30, 60, 90 triangle. We're going to start with degrees just because. We normally do that when we start doing something new, just because we know degrees. So I want to figure out what the sine of 30 degrees is. So it doesn't matter what 30, 60, 90 degree triangle I use. And what do I mean by that? I don't care how big or small it is. It would always reduce to the same ratios. So let me do this. We're gonna prove some shit right now. So let me do this. This is gonna somehow make it easier. I'm gonna start with an equilateral triangle. So the basic question we're trying to ask right now is, what is the sine of 30 degrees? It's got to have a single output like we just said. It shouldn't matter what triangle it comes from. It should just be a brute fact. Sine of 30 degrees equals number. Okay. Equilateral, how big is every angle in an equilateral triangle, considering all angles have to add to 180? They all must be 60 degrees, yes? So you could be saying two things to me right now. You could be saying, hey, crazy ass math dude. I don't see a 30 degree and I don't see a right triangle in there. Okay. I don't know you. It's not what you sound like to me. No. If I draw the height in, what did I just create? Two of. Two right triangles that are what kind of triangles? 30, 60, 90. So I can figure out all kinds of shit, right? Here's the problem though. So it doesn't matter what triangle we use, correct? I can use any equilateral triangle I want to, because it doesn't matter how big or small the triangle is, the ratios would always reduce to be the same thing. Yes? So I'm going to use the easiest one I can think of. 1, 1, 1. Sounds good to me. But what about my right triangle? Is everybody going to, let me see if you guys are cool. I'm going to draw this right triangle turned around over here, yes? Is that cool? This side here, how big is it? It's 1/2, because if I have an equilateral triangle and I draw a straight line down the middle, I'm going to break the base up into half, yes? That makes complete sense. Is everybody cool with the fact that I turned this around as I moved it over? You guys see I took it, turned it, put it, yes? Okay. So this is 1/2. What about this stupid thing? Well, that's easy enough. How do I get this stupid thing? Pythagorean, right? Old Greek dude. The ghost has issues. Okay. So take a minute, I'll wait. Figure out what that last side is. Don't let that fraction scare. We made fractions. Humans made fractions. They work for us. Oh, damn it. Don't you be scared of fractions. Brute force that old Greek dude stuff. If you've taken any trig before, this number you get should look very familiar. If you've never taken trig before, it's not going to look familiar. So here's what the Pythagorean theorem would look like. 1 squared, we call this x for weird reasons, equals x squared plus 1/2 squared, yes? That's a fraction, who cares? 1 equals x squared plus 1/4. Subtract the 1/4, right? 3/4 equals x squared, then I take a square root. For the moment, we're considering a physical triangle, therefore I don't have to put plus or minus, correct? In general, you better. Why this time I don't need to? Because we're only taking the positive. So I get x equals, what's square root of 3? I don't know, what's square root of 4? That's right. So I get x equals rad 3 over 2. It's already got that. So are you with me? That wasn't that bad. Don't give up when you see a fraction. Who cares? Hopefully you guys all got that, because I'm going to erase all this shit. Ready? That's a good feeling right there. Got it. Go away. Just go away. Okay, so coming back to this, can somebody tell me what is the sine of 30 degrees? That's been our question. What's the sine of 30 degrees? It's the what side over the what side. What sine defined basically as y over r. So what's sine of 30 degrees? Y over r. 1/2 over 1 is 1/2. sine of 30 degrees is 1/2. Period. End of story. That just is what it is. What's the cosine of 30 degrees? Square root of 3 over 2. Over 1, right? So square root of 3 over 2. So read with me. That's the x side over the r. And then what's the tangent of 30 degrees? This is going to be a little grosser. Yeah, 1/2 over the square root of 3 over 2, which is 1 over the square root of 3. You've left yourself so much room here, Jeff. Which is rad 3 over 3. You guys see that? The rationalize top and bottom? Or nationalize, whatever I almost said there. You're going to be very excited about this, but you have to memorize those. So I'm going to give you a really nifty way to memorize the sine and cosine facts. And from those, you can build a tangent. If you just memorize sine and cosine, you can build everything else. Can somebody tell me, for example, what the cosecant of 30 degrees is? Frickin' 2! Don't even memorize that shit. Why would you? You can just build it when you need it. That's the way I do it. I don't have that memorized. I can figure it out if you ask me what's the secant of 45 degrees. I can do it, you know. You guys kind of with me? I don't have it memorized, though. Why would I? I can build it as I need it. I only have so much space up here. Okay. I think that's a big mistake people make in general about mathematics is you try to memorize too much. It's all built on basic ideas. Yeah. How are we doing so far? What if I asked you what I'm going to take away some of the stuff, okay? Go away. Get away. Okay. Are you going to think? No. What if I ask you what the sine of 60 degrees is? If you're looking at it that way, you got to look at it this way, yes? So yeah, what is it? Rad 3 over 2. What about the cosine of 60? 1/2. How does the cosine of 60 relate to the sine of 30? Same. How's the sine going over there? Same. What's the tangent of 60? Root 3. Because over 2's cancel when you divide. Is that all right? So now you know sine, cosine, tangent of 30, 60 degrees. Which means you also know cosecant, secant, cotangent of all those things. Yes? Don't memorize the second set of shit, because it's all built off these. In fact, I wouldn't memorize tangent either. And again, I'll give you some ways to make this easier to memorize in a minute. I just want to really set down why these are the values we're going to see. And then I'll give you a nice way to memorize this stuff. Okay, good. I should have enough time to do that. So the other big angle that we're curious about, besides 30 and 60, we're also curious about 0 and 90, but we got to get there. The other one we're curious about is the one right in the middle of everything, 45. So if I set up, Jeff, is that better, Jeff? Sure. Ooh, okay, I'm excited. That's probably my best triangle ever draw. Which is a sad commentary on me. If I set up a 45, 45, 90 triangle, one thing that's nice is it's already a right triangle, right? I had to do an equilateral last time. Can anyone tell me what other kind of triangle this is? Isosceles. Yes. Isosceles. The base angles, if I rotated the base angles are the same, that means that these two side lengths are the same. So incredibly enough, well, let's call this 1 just because. I'm going to use a 1 for the hypotenuse just to make this nice and difficult. And what did we just say is true about those two sides that got little lines through? They have to be the same. And the way I think about this, I'm going to say this a few times. All right, you all know I'm a geek. That's a given. 45 degrees is how open that mouth is. Do you guys see what I mean? So I see this side as the stick that fits in this mouth, And this side is the stick that fits in this mouth. I think about that scene with the Rancor and Luke, and he puts the freaking thing in the mouth. And if you have no idea what it just said, you're fine. Some of you guys know what I'm talking about. Little guy comes out and goes, "Oh no, my Rancor." You say, so, of course, these side links are the same because the mouth size is the same. So these two have to be the same size. So I'm going to put in, don't tell me if you know the answer, but right now, based on everything we know, we don't have a clue how big those sides are. So I'm going to call them X. Why can I call them both X? Because we just said they're both the same size. I could have called them both Y and whatever the shit. Okay. What's old Greek dude say?
Squared plus x squared equals
Yeah, x squared plus x squared equals 1. 2x squared equals 1. X squared equals 1/2. X equals square root of 1/2, which is 1 over square root of 2, which is rad 2 over 2. I did that really fast, and I don't care, because you guys can all do that shit. So I get these two are rad 2 over 2. So what is the sine of 45 degrees? Rad 2 over 2. What's the cosine of 45 degrees? Root 2 over 2. What's the tangent of 45 degrees? 1. If the tangent sine over cosine and 45 degrees, it makes sense that should be where sine and cosine are the same, then tangent is 1. You can see, of course, very explicitly, sine and cosine are the same output, if you know how to read Jeffish. Okay. All right, so some of you guys have taken trig before. These values should look very familiar. I hope to God, whoever taught you trig showed you why those were the values. If not, now you know. It's just the way it is. Okay. So here's the ultimate way to do this. We have a unit circle. Now I want you to know something. I don't care that much about the unit circle. I'm not going to make you fill in a blank unit circle. That is so much bullshit. That is so much bullshit. How much bullshit?
so much.
Thank you. It really is. But it's impossible to speak about trig without, I got it, because that's what this all comes from. That's why a lot of stuff works the way it does. Do you see a triangle in what I've drawn? Not yet. But if I pick an angle, then there's a triangle here, yes? So if I pick, so let's say this is 30 degrees. And let's say this is 45 degrees. Let's say this is 60 degrees. Every one of those, the devil inside, no, Jefferson. Do you see how as I go from 0 degrees, as my angle gets bigger, what happens to the y side? Gets bigger. So of course, as I go from 0 to 90, my sine should get bigger. Now let me ask you this. This is a weird question. You ready? At 0 degrees, what happens to my triangle? And start here. Start here. And do you see how, as I move, it's kind of like somebody's smushing the triangle, smooshing it. So what happens at 0? The triangle gets smushed completely flat. Yes? Then the x side is the hypotenuse. If sine likes y, what should the sine of 0 degrees be? 0. So the sine of 0 is 0. Thank the gods. Sine of 0 degrees is 0. Is everybody with me on that? We figured out what the sine of 30 degrees was. Does anyone remember? I can look at it again. 1/2. What about the sine of 45 degrees? Root 2 over 2. Look at what's happening to the sine. What's happening to the sine as I move? Is it doing the way we thought it should? It's getting bigger, isn't it? You write this better. Jeff, can you for once in your life, write well for once in your life? All right, do it. Sine of 60 we did earlier. Who remembers that? Root 3 over 2. Now, good Lord and a half, Jeff. You just said Oh, I can do more stuff with my eraser? Okay, sorry. Watch this. This is so cool. You don't have to do this. This is nothing. This is nothing. But it's a neat little pattern. Do you all agree with me? It's pretty cool. Sine of 0 degrees is 0, correct? Do you all agree with me that the square root of 0 is still 0? Does anyone disagree? Good, because the square root of 0 is 0. If I divide it by 2, is it still 0? Of course. What's the square root of 1? 1. So did I change the value of that one and put the square on the top? That's still 1/2, correct? Look at what happened. Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2. So what should this be? Going by that pattern. Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2. This should be square root of, no, square root of 4 over 2. What's square root of 4? Divided by 2 is 1. And that makes sense because if I smoosh the triangle this way, smoosh. Oh my God, Jeff. Is there any X piece left? What's happening to the X pieces? It's all gone, yes? It's all Y now, right? So the entire thing is Y. So sine loves it at 90 degrees. Sine is 1 at 90 degrees. So is there a triangle if this angle is 90? Not really. But you can also think of it as I just flattened it. And if I flatten a triangle, let me see if you guys are really cool with this. Doesn't this side become this side? If I flatten it, they become the same thing. So when I do it this way, the x side is the hypotenuse. Cosine is x over the hypotenuse, or x over the radius. If they're equal to each other, cosine is 1. So what does cosine do? Cosine does all this shit in reverse. As I move up, what happens to the x side of my rectangles? Let me just live with that for a second. As I move up my angle, what happens to the x side of my triangles? Keeps getting smaller and smaller. So cosine is going to have the exact same outputs, just in reverse. Are you with me? Okay. I love it. So again, some of you guys already took some trig. It's great. Blah, blah, blah. If you already got this stuff memorized, just sit with that and be really happy. If you've never if you've never memorized this before, never seen it, oh shit, you got to memorize this stuff. Okay. Aren't there 3 other quadrants? Oh shit. So we got to talk about those. The really nice thing, just to kind of lay the groundwork here. What time is it? Yeah, just to lay the groundwork. Oh crap. Just for example, if I have an angle of 30 here, what angle am I really at? Let's say this is 30 degrees. What angle am I really at? 150. You guys with me? So this, but do you see how the sine of 150? I really want you to see how this triangle is exactly the same as this triangle. Aren't they the same frickin' triangle? So all the values repeat. So what's the sine of 150? 1/2. But what's the cosine of 150? One reason you got to be careful. The cosine of 150 will not be root 3 over 2. Why not? Because what's true about x back here? Negative. So you just have to memorize the first quadrant values. Here's the first place SOHCAHTOA sucks major. It doesn't help you with this shit. Sine likes y. Therefore, where will sine be positive when y is positive? Does SOHCAHTOA help you with that? No. Where's cosine positive? Wherever x is positive. Can somebody tell me the quadrants where cosine will be positive? And remember, this is quadrant 1, 2, 3, 4. Because math people are smart. We went counterclockwise. We're really on it. 1 and 4. That's where the x is positive, correct? So, of course, it's negative in 2 and 3. Where are both cosine and sine negative? Both cosine and sine negative. 3. That's where x is negative and y is negative is 3, yes? Blah, 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 blah. Yakety smack. So, in quadrant 3, you'll have angles that have cosine of negative 1/2, negative rad 3 over 2. Everything's negative for cosine and sine. Same stupid numbers, though. Rad 2 over 2 shows up. Rad 3 over 2 shows up. There's just negative in some places. So what it really boils down to is finding this, and I already called that, I already gave that a name. What is the name of that 30? It's really 150, isn't it? That's what the question's going to be about, is 150. What does this little 30 do? Does anybody remember? Man, I really have trouble saying that phrase. Does anyone remember? Does anyone remember? I'm pretty sure I called this what it is. It's the referencing. I might not. Maybe I'll just imagine. This is what's called the reference angle. The resident assistant. No, this is the reference angle. And it's called a reference angle because it refers to the x-axis. If I do the angle that refers to the x-axis, I'm suddenly in the first quadrant again. And I've got all the stuff memorized for the first quadrant. Okay, that's a lot to throw on you, but I wanted to lay some groundwork for next time. We're going to work on, next time being tomorrow, we're going to work on finding reference angles, finding all the trig function values, blah, 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 blah. Okay. That's enough for today, I think. We've done plenty. All right. We'll talk tomorrow about when our next quiz might be. I don't know yet. Okay. I'll see you guys. Let me know if you have any questions.